So first and foremost, may I take this opportunity to welcome you to today's class. Thank you so much. So for today's lesson, we are going to continue from where we left last time. In our last lesson, we looked at the introduction bit of wave 2. Of wave 2. So we are going to proceed from there. So we can make noise. So let me share the screen. So first I'll start by sharing the screen so that we can discuss some of the questions that may arise from the reporter. I hope you are getting me. Is my sound audible enough to get?
Yes.
Ida, are we okay? Are you there? Yes, Ida. Can you put on your videos? Put on your videos first. I want to take the roll call. Put on your videos. Put on your videos. Yes, Tiffany, I can see you are in the darkness. Ida. Put on your videos for around 2 minutes. Ida, your video is not on, eh? Ida, I'm waiting for you. Yes. And then the one using Daniel Oguta's phone. Yes. Alice, baby. Okay. The one for Alice Roylex, I'm not seeing you. Roylex, your video is not on. Roylex, your video is not on. Roylex, are you there with us? Okay. So you can just put them off. So let's start. I'll start by sharing just a minute. Okay. So they said this.
Hii niko hapa.
Okay. Okay, guys. Let me now share it to my Windows. And then the quiz, there it is. Okay. Are you able to see that?
Yeah.
Are you able to see that?
Yes.
Okay. Let's have Diana. Diana, can you take us through the first question? Yes, Diana. Diana there? Is Diana there? Faith, take us through that. The one using Faith.
Okay.
Faith.
What is a ripple tank? Yes.
Yeah, what is a ripple tank? So we had covered a ripple tank. So when you talk of a ripple tank, can you read for us what is it?
Okay. The answer is a simple tank. A simple tank is
A ripple tank.
is a
A ripple.
A ripple tank. A ripple tank is a shallow, transparent tray filled with water used to study wave properties. It produces water waves to stimulate the behavior of other type of waves, such as sound or light, and helps visualize waves phenomena like reflection, refraction, diffraction, and interference.
Yes, so a ripple tank, in fact, I'm going to show you maybe a video of a ripple tank towards the end of the lesson. So it's just a transparent tray, and I hope I've shown you the diagram in our first lesson that is normally filled with water. So in most cases, we normally use the ripple tanks as to study the wave properties. And some of the wave properties that we talked about were reflection, diffraction, refraction, and interferences. So in this case, we are only going to look at the water waves. We are not going to look at the sound waves or the light waves, but all these ones are waves. Okay, so we are going to look at some of the properties of the water waves. Then Tiffany, you can read for us the next question.
How are waves generated in a ripple tank?
Yes, tell us something about it. The answer is there with you.
A ripple tank
Tiffany, are you there?
Nimetoka.
Okay, somebody to pick. Huyo mwenye amesema ametoka. Can you pick?
A ripple tank uses a vibrating motor or an oscillating paddle called a dipper to distribute the water surface, creating waves of different frequencies and wavelengths.
Yes, so a ripple tank normally uses a vibrating motor. So I'll show you how the motor looks like. So it vibrates, and then the motor is normally attached to a bar. It can either be a bar to produce the straight waves, or it can either be a small ball. So the small ball will always produce the circular waves. Okay.
Yes.
And then Ida, you can read for us the next one. Ida, question number 3.
Question number 3 says, what are the main parts of a ripple tank?
Yes. The answer? You can proceed, Ida.
A ripple tank setup includes a transparent water tray, a wave generator, in bracket vibrator or motor with a paddle, a light source above the tank, and a white screen of paper below to project wave patterns.
Yes, so it has got a tank setup that include a transparent water. Okay. So, okay, welcome back, Tiffany. So we have a ripple tank setup include a transparent water tray and also some generators. So these generators are normally used to generate the waves. So I said previously that if it is a straight bar, then it is going to generate the sampling waves. If it is a circular a circular vibrator, it's going to generate the circular waves. Okay. Okay, let's try to move very fast. And then Tiffany, you can now take the fourth question. That's where we are.
How is wave reflection observed in a ripple tank?
Yes, okay, explain it for us. The answer is there.
Place a barrier in the water to reflect waves. When the waves hit the barrier, they bounce back, forming reflected waves. The angle of indices equals the incidence equals the angle of reflection, which can be measured using the projected wave pattern.
Okay. Please ensure that your microphone is muted. You only unmute when I tell you to do that, so as to avoid the background noise. Okay. So, how is wave reflection normally observed? So, when you talk of wave, it's just like the reflection of light. When light strikes a smooth surface, it normally bounces backwards. Okay? It goes and then bounces backwards. So that is called reflection. So when a wave also strikes an obstacle, it normally bounces backwards. So those are some of the properties which we are going to talk about. Then let's look at number 5. Diana, read for us number 5, Diana.
What is a wave refraction and how it is shown in a ripple tank?
So just a minute. Wave refraction, all those ones, we are going to look at them within this lesson. So I don't want to cover that. So I'll take you directly to what we are supposed to cover today, which is okay. Yes. So let me share it again. Yeah. Are you able to see that? Are you able to see that, Ida?
Yes.
Okay, so I want us to continue. So in our previous lesson, we looked at wave. Let me just maximize this so that it looks a bit bigger. Okay, there we are. So we said that waves are transmission of disturbances. So waves can either be disturbances or oscillations, which when they travel from one point to another, they normally transfer energy. That one we had looked at. And then we also said that waves can also be characterized either as periodic in nature, whereby they propagate through a medium within a certain period of time. And for those ones that are able to travel through a medium, we normally refer to them as mechanical waves. But there are those ones that do not require material medium for their transmission. We call them electromagnetic waves. So waves are fundamentals in understanding various phenomena, especially in physics. About the openings, the happenings like the light, the water movement, the mirages, and so on and so on. So we have the two types of waves, that is mechanical waves and the electromagnetic waves, which we have talked about. So that's just a small glimpse on the waves. I think this one we had looked at, the properties. We also looked at the ripple tank. Now, before we look at this one, before we go deep into that, I want to just show you something here. to...
the GCSE Trilogy Combined Science Physics component for AQ.
Are you able to see that?
Hata mwenye tulikuwa tunakuja tunakimbilia hata hajafika.
There's let me just share my screen again. Okay. Now I want us to watch this video. Are you seeing that?
Yes.
So are you people seeing that?
Yes.
Okay, so that is what we call a ripple tank. So inside this, there's water. So let me play the video so that you can see, and I want you to listen to it, because if you don't get it, then you'll miss it out. So try to pay attention this time around.
It's the ripple tank, and as you can see how this works, we have a tank of shallow water. We have a bar of wood. Attached to it we have a motor which has got a weight on it, which means when it spins it hasn't got a correct centre of balance, so basically it creates a vibration, and that vibration travels to the wood and then causes the water to vibrate. We have a light here, and the light projects down, which creates areas of light and areas of shadow. And the areas of light are the tops of the waves, the peaks of the waves, and the areas of dark are the troughs of the waves. So what we can see, and what we expect to do with this core practical, is we're expected to then make a measurement of wavelength. So if we look at the pattern here, you can see that you've got areas of light and areas of dark. So if we measure from an area of light, which is the peak of the wave, to an area of light again, the next area of light, which is the peak of the wave, that is our wavelength. Sometimes it's quite tricky to do. It can be improved slightly by using something called a stroboscope, which creates pulses of light, which helps it may appear like it's moving slower. If I turn up our power here, okay, to a higher voltage, it will make the motor move faster, and so it will increase the vibrations, so it will increase the frequency. Now we know that frequency times wavelength equals the speed of the wave. The speed of the wave is going to remain constant, so if the frequency goes up, the wavelength will go down, and the waves will get closer together. So let's try that. We're going to turn up the frequency, and now the waves are now closer together. And if we continue to turn it up, we can make the waves even more closer together. So that's the required practical for physics, and you'll be asked to describe this, and you'll be asked in an experiment to make measurements of the wavelength by going from peak to peak.
Okay, can you listen to that?
Hizo maklasi wote na nikijaribu connect na DT haiendi na.
Who is that talking? The one using Daniel. Daniel, what's the problem?
That's class representative.
Yes, that's class representative. What's the problem? You are not, have you seen the video?
Yeah.
But I've heard you complaining that the classes are not going through.
Msisha huyo ni Aida Nekesa, si mimi.
Okay, Aida. Aida. Is Aida there? Aida?
Tell me I've not talked, Simaji. Sijaongea.
Huyo ni Aida.
Hiyo ni mimi. Sijaongea. Diana.
Yeah.
Sijaongea.
Ni Aida Nekesa.
Okay. There's no problem. Let's just continue. It's okay. When you are talking, try to unmute so that we don't get what you are saying. maybe we may be hearing your secrets. Okay, so let us go back to our slide. I hope you are able to see the video, you're able to see the ripple tank. Now you know more about the ripple tank. Is it true?
Yeah.
Yeah, so you've seen now the vibrator looks like. So that when I talk about a ripple tank, I'm not talking about Greek. So, Diana, the class rep, take us through this.
As the motor vibrates, the bar attached to it makes plane waves on the water.
Yes. Yeah, just continue.
Since the bottom of the tray is transparent, the light casts an image of the passing waves on the screen at the bottom. A spongiform material is lined on the tray to absorb the wave and prevent it from being reflected back.
Yeah, so as the motor vibrates, there's always a bar that is normally attached to it, and you're able to see the motor. So when you attach a bar, it will produce what is called the plane waves. But if you attach something like a ball, it will produce what? The circular waves. So since the bottom of the tray is normally transparent, you're able to see through, and then you'll be able to see some regions that are dark and some regions that are bright. From the video, you're able to see those regions, is it?
Yeah.
Yeah, so those regions which were bright represents the crests of the waves. Remember, the crests normally moves upwards, displacement. And then we have also the regions that were showing dark, which were the troughs, which normally displaces downwards. Though you are not able to view the movement, the displacement, but you are able to see the regions that are dark and the regions that are bright. That's what is normally being observed in ripple tank experiments. So if you are asked to state the observation, you talk of regions that are dark and the regions that are bright. And then there's a spongiform that is normally placed that is lined on the tray. So the work of the sponge is to absorb those waves that might be reflected, so as to give you that clarity. So it reflects those waves that are reflected. And then the continuation, Tiffany, take us through this continuation. Tiffany, is there Tiffany with us?
The crest appears bright while troughs are dark due to refraction of light. To produce circular waves, the bar is replaced with a small spherical ball. However, it's often difficult to follow the continuous waves across the screen, hence a stroboscope is used to slow down the motion. The wave pattern is represented by wave fronts line.
Yeah, so there's always a crest that normally appears bright, and the regions that are dark are the troughs. You will correct that. While troughs, not troughs, should be T. Troughs are dark due to the refraction of light. So if you are asked to explain what the bright region represents, you talk about the crests. What does the dark region represent? You talk about the troughs. And then when do we produce circular waves? When you use a small spherical ball. When do we normally produce straight plane waves? When you use a straight bar, you produce the plane waves. However, at times it is more normally difficult, yes, so as to follow the waves. You're able to see how those regions that are bright and regions that are dark, the way they are moving very fast. So it's sometimes difficult. So what we normally use, we use a stroboscope so as to slow them down. And you're able to see how the man could slow down the wave motion so as to take the reading. In fact, the most important reading here is the distance between those regions, the dark and the bright regions. That one will give you what is called the wavelength. Now, I hope you're able to see my screen here. Who is this calling in the group and yet we are here? So will you? Just a minute. Let me just sort this person. I don't know whether they want to. Tumeshaanza.
Ujua nimeunmute. Lakini hizi.
Oh, this is Abigail. Oh, we Abigail.
Are we supposed to be eating these things?
Okay. Class, are you there?
Yeah.
Okay, let's look at those wave patterns.
Right.
Yeah, we have the crest. Are you seeing the crest and the troughs?
Yeah.
So the distance between this crest and trough give us what is called a wavelength. Okay. So wavelength, the distance between those stakes. Any distance between them give us what is called wavelength. And you can see it has been traced there. Yes, Abigail. Hello. Yes, how are you, Abigail? Hello.
Sina call. Aongee.
Hello. Okay. Let us continue. So you can see we have crests here and then we have troughs. We have crests and we have troughs. But when you look at these straight lines, they represent the crest, 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 crest. So if I find the distance between these lines, I'll be getting what is called the wavefronts. The wavefronts, which are the same as the wavelength, is the distance between crest and crest, crest and crest, crest and crest. Or somebody may talk of trough and trough, trough and trough, trough and trough successively. So I hope you have gotten that. We can move to the next slide. Any question? Somebody with a question?
She's always raising her hand.
There's somebody who keeps noting on what people are doing. Okay, the lines. Now, on the lines represents the crest. Yes, Diana, continue.
The lines represent the crest, while the halfway between any two successive lines are the troughs.
Yes, so the distance between the two successive wavefronts is equal to one wavelength. Now, there's a question there, which I would like you to look at. Tiffany, read for us that question.
The figure below shows a sketch of ripples caused by a vibrator in a ripple tank whose frequency is 50 Hz. Determine the speed of the wave motion.
Yes, determine the speed of the wave motion. So I want us to get the speed of the wave motion. And how are we going to get the speed of the wave motion? First of all, we have to know the distance and we have to know the time. Now, Diana, we have the frequency to be 50 Hertz. Can you calculate for us the time? What is the time? If frequency is 50 times tapataje, haraka haraka.
Zero 0.02.
0.02. Umefanya nini?
I have taken 1 divided by 50.
Good. 1 divided by 50, 0.02. That's good. So we have 0.02, 1 divided by 50. And then you have to count for us to get the total time, you have to count this. Like when you look at the distance that we have been given, it is 24 centimeters. You have to change this 24 centimeters into meters. So you are going to divide this by 100 so that you get 0.24. And then time will be the distance of separations. How many spaces are there? 1, 2, 3. So there are 3. And 1 is 0.02 to get time. So you multiply by 3, you get 0.06. So you have 0.24 divided by 0.06. So your speed will be 4 meters per second. 4 meters per second. Good. So the next thing that I want us to look at is rectilinear propagation of waves. And rectilinear propagation of waves. Huyu Alice, hebu nisikie nini voice ya nani Roylex. Roylex, take us through rectilinear propagation of waves. Is Roylex there? Class rep, is Roylex there? The one using Alice. Hebu angalia kama huyo mwenye anatumia Alice ako. Faith.
This is the property of waves to travel in a straight line and perpendicular to the wave front. Plane waves are produced by a rectangular bar while a circular wave is produced using a ball.
Yes, I want you to look at that that rectangular bar. You can see it is producing some of the waves, the straight ones. These straight ones here are what we call the waves. So we have this bar, and then it is producing these plane waves. These straight ones are what we call the plane waves. So as these waves move, okay, you can see they are moving along a straight line. So there is this path which has been drawn, which is straight. So it means that these waves are moving along a straight path. So that's what is called rectilinear propagation of wave, meaning that wave can only travel in a straight line. Just like the way we were talking about rectilinear propagation of light in Form 1, where we said light can only travel in a straight line and it cannot go round, okay? So in case of a circular bar or a spherical ball, it will produce some circular waves, and these waves will travel in a straight line, and you can see they move straight. Okay, so that's that. You can continue. If a cork is placed, Diana, continue.
If a cork is placed on top of a ripple, in brackets wave, it moves up and down
Rhythmically,
but it remains in the same position.
Yes, so if you are supposed to place a cork on top of the ripple, the ripples, that is the waves, here you'll find that it moves up and down. Why? Because this wave, as it travels, it forms some regions of crest, troughs, crest, troughs, crest, troughs. So that's what will make it now move in that direction. And then Diana, reflection of plane waves and circular waves. That's our next subtopic. Continue. Diana, continue. Is Diana with us? Okay, Tiffany.
Plane waves on an oblique angle reflector. The reflection of the waves obey the known law of reflection of light. Example, angle of incidence is equal to the angle of reflection.
Okay. With this, Tiffany, but Abigail. Yes, how are you? Yes, what's the problem? Why is it that you are calling me on WhatsApp but you cannot join?
I don't know what is the problem.
See, those are links that I've just sent. Are you seeing a link that was sent written Google something? Leave alone the form.
Yeah.
Have you pressed on it?
Yes.
Ebu press on it again so that I can admit you. Ebu press on it. Okay.
Minutes na left class. Mwanyo data maruana wakende.
So that one has left. We are almost ending the meeting, and there's this girl who really wanted to join, but it's like she has problems. So let us just continue. Yes, Tiffany, continue. So we have Tiffany. We have talked about the plane waves on an oblique reflector. So you'll find that when the wave moves, they normally move in a straight line, and there's this object which has been placed in an oblique angle. So when an object is placed this way, what normally happens is that the incidence wave gets reflected such that the angle of incidence is equal to the angle of reflection. So these two angles are always equal. So if you are to draw this, you'll ensure that you use a protractor so as to measure the incident angle and the reflected angle. So this is how the wave will move. It will strike this obstacle and then moves downwards that way. Then, the angle of incidence must always be equal to the angle of reflection. Now, let's have a situation whereby we have plane waves traveling and then they meet a reflector at 90 degrees. Okay, Ida, can you read for us that? Ida? Is Ida there? Ida? Okay, Faith, take us through it. The one using Faith.
Plane wave on straight reflector at 90 degrees. It
Yes.
goes the wavefronts are reflected back through the same path as plane waves.
Yes, you can see as these waves are moving towards the obstacle. So we have the straight ones, leave alone the dotted ones. The ones which are moving to the reflector are the straight ones. And then it strikes this plane and then moves backwards. So the dotted ones are the ones which are now moving backwards. So this one tells us that when we have plane waves moving towards a straight reflector, once they strike the straight reflector, they get reflected backwards. Okay, so they are still plane waves, even though we are representing them using dotted lines, but they are still plane waves. So nothing has changed. Nothing has changed. Now, what of if we have the plane waves? So we've talked about this one, plane waves on a straight. Now let's look at plane waves on a concave reflector. So this time round, we are going to look at the plane waves, but on a concave reflector. Yes, the one using Bebida to read us for us. Yes.
Plane waves on a concave reflector Reflected wavefronts are circular and converge at a focal point in front of the reflecting surface and then diverge. Hence, a concave reflector has a real focus.
Yes, so we have the reflected wavefronts are normally circular and then they converge at a focal point in front of the reflecting surface and then diverge. Now, if you are to look at these straight lines, these are the plane waves. So we are directing them towards a concave reflector. So once they strike this concave reflector, then they come backwards as circular waves. You can see these dotted ones, which are coming backwards. So they come backwards as circular waves, and then they converge at a certain point here. They meet at a certain point, after which again, they start diverging as they move outwards. So that is the behavior of circular waves. That's the behavior of the circular waves. So if you are to, in fact, you are supposed to know how to draw these. You should know how to draw this one, OFED. You should know how to draw it. So that's something which is very, very important. Next thing is, and then I'm recording this video. You can tell those ones who have not attended the class, I'll share it through your WhatsApp immediately after this. Okay. Then we have plane waves on a concave reflector also. So we have, there's a difference between this one is a concave reflector, this one should be a convex reflector. Yes, these are convex reflector. So there's a difference between a concave reflector, which I want you to observe. Look at this, is curved. That's why we call it concave. And then this one is bulging outwards. Look at this one, it is bulging outwards. Tiffany, are you able to see the difference? Tiffany?
Plane waves on a convex reflector. The waves appear to be diverging from a point behind the reflector. This point is the focal point of the convex reflector.
As you can see, these are plane waves. So they move towards this convex reflector, which is bulging this way. So once they strike it, they change again into circular waves. But now these circular waves, they are coming from a certain point behind. It's like they are seen as if they are coming from a certain point behind the convex reflector. So that's why they move in this manner. So they get reflected. So there are certain things which you are supposed to note here. And I want you to be very, very careful, because in most cases you'll be asked to draw these. Now, I want you to look at where we started from when we were directing plane waves. Plane waves, when directed to an oblique surface, they get reflected such that the angle of incidence is equal to the angle of reflection. Oblique surface. The next one, we directed it on a plane straight surface. Unaona bado it is still plane waves. It is still straight, plane surface. Then plane surface still the same. And then now a concave reflector. So this wave, they are straight, but when they strike the concave reflector, they now become circular, and then they converge at a point. Okay? Then again, on a circular, but now this time around a convex. How is this wave behaving? They are coming, they are as if they are coming from a certain point. It's as if they are coming from a certain point. You seeing that? So those are some of the differences that you're supposed to note in this. You're supposed to note those differences. Very, very important. I think we have come to the end, but before that, I want you to just have a look at this one for the second time, please. And then I'll tell you the next direction. Let's have a look at this for the second time.
AQA and the GCSE Trilogy Combined Science Physics component for AQA. It's the Ripple tank, And as you can see how this works, we have a tank of shallow water. We have its AQA and the GC.
Just a minute. Let me share it for the last time and then we stop after that. Gosh. Let me share this. No, it's not working. Okay. Are you able to see that? Are we together?
It's the Trilogy Combined Science Physics component for AQA. It's the Ripple tank. And as you can see how this works, we have a tank of shallow water. We have a bar of wood. Attached to it, we have a motor which has got a weight on it, which means when it spins, it hasn't got a correct center of balance. So basically, it creates a vibration. And that vibration travels to the wood and then causes the water to vibrate. We have a light here, and the light projects down, which creates areas of light and areas of shadow. And the areas of light are the tops of the waves, the peaks of the waves, and the areas of dark are the troughs of the waves. So what we can see, and what we expect to do with this core practical, is we're expected to then make a measurement of wavelength. So if we look at the pattern here, you can see that you've got areas of light and areas of dark. So if we measure from an area of light, which is the peak of the wave, to an area of light again, the next area of light, which is the peak of the wave, that is our wavelength. Sometimes it's quite tricky to do. It can be improved slightly by using something called a stroboscope, which creates pulses of light, which helps it may appear like it's moving slower. If I turn up our power here, okay, to a higher voltage, it will make the motor move faster, and so it will increase the vibrations, so it will increase the frequency. Now we know that frequency times wavelength equals the speed of the wave. The speed of the wave is going to remain constant, so if the frequency goes up, the wavelength will go down, and the waves will get closer together. So let's try that. We're going to turn up the frequency, and now the waves are now closer together. And if we continue to turn it up, we can make the waves even more closer together. So that's the required practical for physics, and you'll be asked to describe this, and you'll be asked in an experiment to make measurements of the wavelength by going from peak to peak.
Okay, so let's mark the end of our lesson today. I'll send the video to the WhatsApp group. So ensure that you go through that video clip. And then there's an announcement that I want to make. Those people who have just left, there's an announcement that I want to make. Our next lesson will not be there next Sunday, so it will be the other Sunday, not this coming Sunday, because this Sunday I'll be attending a marking session that is the KCSE exam, that is physics paper 1. So I'll not be able to project these lessons. So we will not have our next lesson. So we'll rest next Sunday and then maybe proceed in the other Sunday in case I'll be around. I'll always communicate. Ensure that you go through the WhatsApp group so that you get the information the way it is required. Otherwise, thank you. Thank you for attending the lesson. I've really appreciated so much. Continue attending the lessons because I don't think if we'll go through some of this topic again because of time. So for those who have not yet attended the lessons, please ensure that you go through the video clip. It will be there in your WhatsApp group. I'll also upload it on YouTube. So you'll just search Ongeti Martin and then you'll be able to find that video. Otherwise, thank you. You can have a good day, a good night. Thank you. Thank you, Ida. Thank you, Roylex. Thank you, Faith, the one using Faith, the one using Tiffany. Thank you so much. So you are free. We can just end the meeting. Thank you.